Okay, now for something a little connected and a little different. I'm going to go out of the box as a scientist and talk about life and its possibilities, because however weird you think your particular life may be, or I think my life may be, life on Earth is definitely weird. How we got here is weird, and that's a subset of the total weirdness. I guess we don't have sound. We're missing sound on the... There we go. So what's really going on in astronomy is we're waiting for maybe the last shoe to drop in the Copernican revolution. So if you want to make sense of the history of astronomy since Galileo and Copernicus, it's basically that the intelligent designer, whoever he or she may be, is telling us we're not special. Get over yourselves. And the last way that we may get that message is by learning that we are not unique as biological entities on this planet. Astronomers are also have in their hip pocket the possibility of demonstrating we live in a multiverse, in which case everything I'm talking about tonight you can scale up by the number of universes there are out there. But basically that's the most exciting and pivotal question sitting in front of astronomers right now is the search for life in the universe. But we still have to reference everything back to the Earth. And we have, so that's just one narrative. There is only one form of life in the universe as far as we know. So we have to draw as many conclusions as we can from life on Earth. And that's difficult because what we really want to do is ask what might be but isn't. What we really want to do is wonder how strange it might be, because there's no reason that this particular story that we're all a part of and we're kind of attached to, for obvious reasons, is the only story out there. Or even, it might not even be the best story out there. Let's hope it's not the worst story, but it's just a story, and there are very powerful things. Science works by testing ideas, hypotheses, data, and so on. But I think it's a very underrepresented part of science, because it doesn't fit quite neatly into the standard paradigm, that scientists look about what might be. So I can simplify enormously and say that there are things that are and there are things that aren't. And then there are the things that are possible, most of whom, hopefully, the things that are possible. The tricky part, both as a scientist and as a human being, is that there are things we can imagine. Now, I don't think we're actually smart enough or clever enough or creative enough to imagine all the things that are. We can imagine a lot of the things that are possible, and we probably imagine a lot of things that aren't. And in science, for those of you who may have not thought of it as a purely creative pursuit, we're stuck with this problem too, that we can imagine things that we can't find, that we can't test, that we can't yet discover, but it's a fruitful exercise. So we have to work with our imagination. When I was asked to go out to northern India and teach Buddhist monks cosmology, I didn't want to make any undue connections with their discipline. I wanted to speak out of my training as a scientist, but of course I was extremely aware that science is a unified entity, and that the strangeness that occurs on the biological scales is at the logarithmic midpoint between the micro and the macro. And that is epitomized by the Ouroboros. And this is not just a metaphor or a representation or a nice diagram. It means that the only way we can test the theories of the very large are with theories of the very small. The Big Bang essentially is the iota of space-time where we discover the fundamental nature of matter as well as the nature of the entire cosmos. It can be done with telescopes or particle accelerators, but probably the exciting stuff in physics is happening where the tail disappears into the mouth of the snake. So I was interested in play, because if Zoob is just a toy, then science is just play. And so in addition to Zoob, I took out a big lot of Zoob with me to India and I was grilled by customs. They didn't know what it was. They thought there was drugs somewhere involved in it, but they put me in the room for a couple of hours. I also decided to initiate the idea of open-ended play. I created a deck of cards. I have one example here, and each of the monks got one, and we were playing with them. And one suit of the cards, they were just sort of made-up cards. These are the cards that represent the scales of the universe, and because I'm a cosmologist, I had to throw in the multiverse there. But there were basically four suits. There were the matter, there was the universe itself, objects in the universe, there was radiation, and then there were the biological suits. And we basically, with no rules and no real idea of how I'd work with them, we invented games to play with these cards. Sometimes they were just sharing games, sometimes they were competitive, sometimes they were group games. So we didn't have a taxonomy, we had no idea. I decided not to go out with fixed ideas. And the monks and I decided how we could use these and intercompare all these aspects of the universe through the game of these cards. And Zoob was another extremely fruitful way that I engaged most of my material, which went back to the fundamental aspects of physics as well. So I started with physics, and I started with the idea that the universe, as we understand it, has four forces of nature, very different in scale, very different in strength. That's necessarily not the way it has to be. I mean, there are other universes out there. As E. Cummings said, there's a hell of a universe next door, let's go. And that hell of a universe next door might have completely different laws of physics. So Zoob was interesting because it accommodated the diversity of forces in nature. It allowed me to make a grid of interaction strength using its component parts. And so we played with sort of hypothetical physics just by using the fundamental entities of Zoob, just the basic elements, the simplest components themselves. Then we moved into the idea of chemistry, which is the combination of atoms. And the universe we live in has some interesting properties. The universe is basically made of star stuff, sun stuff. So if you ask what is the universe made of, it's the left-hand column. Where carbon, the thing we treasure, the thing that we're constructed most interestingly of, is a trace element in the universe. Humans overrepresent carbon, nitrogen, and oxygen by a couple orders of magnitude compared to the universe as a whole. And that's interesting too, because it says that our story is the story of stars, because every carbon atom in your bodies, in my body, was produced by a star that lived over 4.5 billion years ago, because that carbon pre-existed the Earth, the Sun, the solar system, and your bodies. So there's a narrative of elements being churned in and out of stars. It's a cyclic process. If stars were selfish and collapsed in on themselves and trapped their ingredients, and there was no recycling into the medium between stars, then also we would not be here. So the issues of chemistry and star formation and star birth and death are fundamental to the existence of life in the universe, and they root into nuclear and atomic physics. So there are certain issues there that physicists have decided almost amount to coincidences, and physicists hate coincidences. Of the elements in the periodic table, there are roughly 24, 20 or so, that life uses. So biology, as a more complex scaling going up from chemistry, is highly selective. It's selective in almost every aspect. And so we experimented, we played with Zoob, and we looked at the possibilities of a yellow-only universe. So just after the Big Bang, a few minutes after the Big Bang, the universe, being as hot as the center of a star, had created helium from hydrogen, and that's all there was. Again, if the universe had expanded somewhat faster than it did, and stars hadn't been able to congeal from gravity, that would be the end of the story. Because if you have a universe with only hydrogen, which can just join in a sort of referential way with itself, or helium, which is inert and can't join with anything, you have a dull and biologically bereft universe. So we looked at the possibilities which could be sterile, a yellow-only universe. We looked at the possibilities of other universes where the structures that can form are more interesting, more complex, and of course more scalable, almost to infinite complexity. And that's what happens when you get carbon from stars. So we played with all this without putting names to it, without saying that it had to be part of anyone's particular story. And also you can combine the same ingredients into entities that have quite different secondary properties. So just as the Greeks speculated that there were fundamental entities of nature by doing the logical thought experiment of dividing the grain of sand over and over again and asking whether you prefer that that sequence continue forever or that it reach an end, the secondary components that are made from those atoms have very different properties. And so we moved into biology. And in biology, my son, I took my 15-year-old with me to India, and everything you'll see in the next few slides emerged from my son while I was off teaching, and I'd come back into the chaos of our little room and find the things that he had made with Zoob. There were no instructions, he didn't know what it was, he'd never seen it before, I'd never seen it before. So this is what I would come back to after I'd been teaching. He'd create these rigid structures, he'd create flexible, permeable structures. He would create repeating structures that, of course, you could use to fill a universe with or create a reference grid for a universe, some of which had higher or lower degrees of symmetry, but all of which could be scaled essentially infinitely. And basically, this is what happened. I came back exhausted from lecturing, and then I would have to play. Oh my God! Well, lecturing was actually playing, so that wasn't too bad. So again, just showing you what my 15-year-old came up with while he was sitting there in the room for a while. And some of these have biological implication, of course. When you have membranes that are permeable or semi-permeable, when we have self-referential structures that can fold over on themselves and become more complex, then you have the rudiments of what we think happened on Earth 4 billion years ago. Some simple units, have enormous possibility because they have, because they're malleable. So some are rigid, some are malleable. The malleable ones can be compressible or amorphous. And the nature of objects around us is a mixture of regularity, chaos, amorphousness. And some of them are just beautiful, and that's as it always should be. So when I was talking about biology, I did want to make some references to the tradition of the place that I was staying. And I think the connection is extremely strong, because all life, if we've learned anything from modern biology, from the sequencing of DNA and RNA, is that we are all